So I'll give the floor to Greg and appreciate your time.
Yeah, good evening, everybody. Thank you for the invite. So as he mentioned, so my name is Greg Gorbett. I teach at Eastern Kentucky University, so it's one of the only degree programs in the United States that offers a degree specific to, essentially what we do is fire and explosion investigations. So it's a bachelor's of science. And I've been there for 18 and a half years now teaching. Prior to that, I was a full-time fire and explosion investigator. And since then, over the last 18 years, they encourage us to consult. So I also have I had my own company for a long time, and then I just became an affiliate of a larger company called Secretariat. So I also still work in the field as a fire and explosion analyst. Yeah, I got all those certifications and stuff that I'm pretty sure most of you also have through NAFI and IWI. My focus, so I did my PhD in fire protection engineering, but, ultimately I always wanted to use the science better to understand the forensics for fire. So even though I've never done the design side of stuff other than as it applies to the forensic side of things. But the majority of my research, I just kind of threw some papers up here. Majority of what I've done is I focus a lot on better understanding, how can we use the damage after the fire in relationship to the science that would have caused it. So what are the fire dynamics that are really causing the patterns and what's affecting that? So most of my papers have been kind of in the area of fire patterns or the understanding of fire dynamics with patterns in mind. So there's some articles if you want to, short cure for insomnia, you can read any of those. But that led us to kind of where we're at right now. We got at Eastern Kentucky University, we got a federal grant through the United States, National Institute of Justice. That grant allowed us to kind of pursue an avenue of research that I was very interested in. And you'll see me talk about this later a little bit more, but I'm very interested in how can we make our forensic science more objective. Because right now, when I started 20-something years ago, it was very subjective, and I think it still is very subjective. And, they always say art's in the eye of the beholder type thing. So what can we do to make our interpretations and what we see more reliable and more objective that you and I kind of agree on what we're seeing? And so that's kind of been a lot of my focus over the years, the last, decade or so. So one of those things is how do we do a better job of getting measurable data? We wanted to focus on that issue, and really there had been some prior work on drywall and depth measurements, and we're not far above the monkeys where we're sticking tools into stuff still, but it does seem to be one of the better objective methods that we have in fire investigations. So we wanted to pursue that and see if there was a better way, mathematically and experimentally, that we can tie together what we're seeing, what we're measuring, and then ultimately can we predict, based on different origin hypotheses, what kind of damage to expect. So that was kind of the goal behind this, is we wanted to do more experimental work on gypsum wallboard and drywall for depth measurements. We wanted to tie that into patterns, and then we wanted to see, is there a mathematical relationship that we can use that's useful to a fire investigator to better do this job. So that's kind of the overall trend. We got 4 years of federal grants. It was 2 different grants that we received. The first one, we focused on regular drywall. And then the last 2 years, we've been focused on the different types of drywall, and we'll go into a little detail on what that means. But really what we were trying to tie together is there a way from the forensic side, the data that we gather through depth measurements, is there a way we can tie that back into the fire dynamics? And then the better we understand that, the better we'll understand the fire investigation. So it's a big cycle is kind of what we were focused on. The objectives basically, we want to analyze gypsum calcination or drywall, the depth measurements in drywall, and then can we predict that? There's a lot of challenges with that. If you just assume it's regular drywall, just by itself, there's a lot of challenges because we don't know from a chemistry standpoint exactly how that dehydration front is going through the drywall. And so let me back up. So when I talk about drywall, gypsum wallboard, I assume it not translates, but it's kind of the same words you guys use over there. It's a predominant lining material that we run into in the United States. I used AI for this, but it also said, and you guys can correct me, is Australia and New Zealand in that area, you guys use a lot of drywall as well for your lining materials?
We call it, I had a blank, but we've got a brand name. We call it a brand name rather than drywall. Plasterboard.
Okay, so like
Gyprock.
Gyprock. Yeah,
Gyprock, okay.
Yeah.
So there you go.
Plasterboard.
Thank you. So that's kind of the same stuff that we see in most of our structures over here. Now we'll get into, we have block walls and stuff and reinforced concrete, but a lot of our, especially residential, and a lot of our commercial structures will still have drywall. So we run into drywall a lot, or gyprock a lot in our structure fires. So we wanted to kind of focus on that. So here in the States, and I'm assuming it's very similar over there, you basically have two pieces of craft paper that sandwich together the gypsum material. In that gypsum material, there is, and we'll get into the chemistry just enough not to hopefully bore you, but there's chemically bound water. And so that chemically bound water, what happens when we heat it? Well, it has to get dehydrated, but it's also now a dehydration front as this heat transfers going through the material, which is what makes it such a good lining material from a fire resistance aspect. That's why we use it quite often over here, and I'm assuming that's why you guys use it there. But the chemistry of how that dehydration front moves through wasn't very well known. So we had to do some deep dive in some of the chemistry to better understand from a modeling standpoint how this would actually work. So anyway, those are some of the challenges. So I'll get into the basics. So we focused our initial investigation, so we'll call it phase one, just your normal gypsum wallboard, not lightweight, not anything different, just kind of a homogeneous mixture of gypsum drywall that we would normally run into here in the States. And then the second half you'll see I'll talk about is basically the other side of that. So we looked at fireproof, water or moisture-proof board, sound resistant, those types of gypsum wallboard, and lightweight, where you have just basically pockets of air throughout. And we wanted to see, first, just regular drywall, how does that, or gyprock, how's that affected? And then secondly, the last 2 years we've been focused on, well, can we see a similarity in these other types of drywall? So just to back up, gypsum, gyprock is essentially 21%. This is your normal gypsum wallboard, or gyprock is normally 21% by mass chemically bound water. You also have some absorbed free water just from your humidity and just kind of moisture in the air anyway. So the way gypsum calcination works is you have this calcium sulfate dihydrate. So that's where your chemically bound water comes in. As you heat it, you essentially have to chemically dehydrate the wallboard or the gyprock before you really start affecting the material itself. So we're going to look at some of the chemistry. That's about as deep as we'll go at here. And then we used a depth caliper, and I'll go into a little bit more detail on how this was constructed. This came from Jamie Novak, who was a fire marshal in Minnesota, and he developed a better way of reliably doing these measurements. But I'll show you kind of the different methods that were out there. So that's kind of the basics to gypsum calcination. As the fire's heating the wall, we're dehydrating it, and by that dehydration, we're leaving kind of this crumbly material behind, in which fire investigators, we can measure that And what we're looking at is it reliable as a measurement for us? So the original work, at least in the United States, was by a group. It was a husband-wife. She was an electrical engineer. He was a fire investigator. And they were the first ones to kind of publish anything about, this potential of being able to look at gyp rock, and through the heating, can we measurably determine what's going on? They initially actually did cross sections, so they would cut the board and then they would look for bands of different color. Well, it's hard enough to have fire investigators poke sticks into the wall. Trying to have them cut little sections of drywall throughout the whole scene isn't going to happen. It's just not, that's not a feasible task for a fire investigator, just the time aspect of that alone. So then what they moved towards after the 1980s was, can we insert a probe and get a depth measurement that's going to give us that similar context as what they were getting with the changes in color. So we initially started, and I'm assuming you guys all have something similar in your own fire scene kits right now, something with you need a blunt end instrument. So you can't, or probe. So you can't use a knife because that's actually going to pierce into the still hydrated drywall or gypsum. So you need something that's blunt end, that's not going to force its way through. The top probe here, if you're interested, you can go on Amazon. What we use these still, but I'll show you other tools here in a second. But most of these you can buy at any local hardware store. Something with a blunt end probe usually does the trick. The one on the top, though, that is technically a depth probe for measuring the thickness of fire resistant material. So like your foam insulation on your steel members. So that's, if you're wanting this instrument, then that's a way to find, is Amazon or similar online store will have those. We moved to this tool. And the reason we moved to this tool is we wanted to be more reliable, because the original tool, it really depended on who was pressing, right? What kind of force was behind. So if you got Bubba over here who can bench like 400 pounds, is he kind of pushing way much harder than somebody else? And so what we were trying to do is figure out, is there a better reliable measuring device? And we came up with a whole bunch of them. You'll see a couple pictures later that nothing really ever worked. Like, we wanted a constant spring to allow that to take the user out of the pressure aspect of it. And Jamie Novak, who was, like I said, a fire marshal in Minnesota, came up with this idea. And basically, he just takes a PVC tube. He takes your digital probe, which you can get, your tire probes or just a general caliper will work, and then just a spring behind that. So I have this in a PDF document. Sadly, Jamie Novak's passed away, but he provided me how he kind of built these a long time ago. So he was always okay with me sharing that. So I can share that with you guys so you can kind of see. It's by picture how he breaks it down all the way, but you can kind of see here. It's pretty simple construction, but again, the purpose was to see if we can keep this a reliable measurement, regardless of who's doing the measurement. So just from a fire investigation standpoint, this might be review for most of you, just kind of how we do it here in the States. You're pressing into the drywall, either with the digital probe that I just showed you or the original, by hand probe. We typically grid the walls so that we have a uniform measurement, system across a wall surface. And so we use, usually we'll mark the score of the wall with some tool, and then we'll come through with chalk lines and pop the chalk lines, which kind of give us a visible grid. And then we measure wherever those grid lines cross. That's a pretty labor intensive process. Just chalking that many lines takes some time. So what oftentimes I do, especially if I'm on a scene by myself where I don't have an extra set of hands to help, I'll just take the surveyor's tape, the pocket rods, the ones that pull all the way out, that go to like 6.5 feet. I'm assuming you guys have that as well. where they'll pull completely out, and I'll just hang those off the wall, and that essentially is kind of my vertical grid, and then my horizontal grid I'll just lay a tape measure, and then I'll go foot by foot. Nobody's done the true measurement system on do we need to do this 6 inches by 6 inches or a foot by a foot? How refined does that grid or mesh need to be? Nobody's done that work yet, but 1 by 1, 1 foot by 1 foot, what is that, 0.3 meter by 0.3 meter, is usually adequate for what we've seen so far. But we establish a grid essentially just to kind of make sure that we're measuring in similar locations throughout the space so we can have an idea of what's going on with that. Now, just back up a second. The whole point of the measurable data is a pattern, right? Do we see a pattern in the damage? And so sometimes, in this case, the picture in the middle is pretty simple. You can see your clean burn, that white discoloration here in the center of the wall. And that's substantially more damage than the surrounding paper that's just kind of charred. You're getting that paper to start to peel, bubble, and flake off as well. But that whitish discoloration has burnt that completely off. So just visibly, we can probably tell you right now that that's the greatest area of damage. Where we found depth of calcination being very helpful is if the whole wall is black or the whole wall is white, because we can't see from a visible standpoint any differences, but measurably there are some differences, and I think that's where fire investigations can really benefit from this. So we've been doing tests. So I've been doing fire tests ever before I got to EKU. So for the last 20 years, I've been involved in doing fire patterns test, and so this is one of our early on tests. We started the fire in the center of the bed, and then we were looking at the damage afterwards. Obviously, you have your clean burn, so it's pretty simple to kind of see what's going on here. But then what we did is we measured it, or we gridded it off, and then we measured it. And this is how we would, back in the day, would display it for everybody else to kind of follow along. Now, what I have been doing is using Excel, or I use MATLAB quite often because it's just a matrix of numbers just to help give us a contour plot, which looks a little bit nicer. So I'll kind of walk you through that here in a second. But what I want to show you now is we did a series of tests. So we've been doing tests for a long time is what I'm getting at. And we've been taking depth measurements for a long time too. So for instance, this would be to me an example of where doing depth measurements are helpful. So we perform this fire test. We have a love seat underneath the window, and you have a door as a ventilation. So you can see the wall damage here. It's pretty much all high, right? Nothing surprising there. I don't think an origin's over there. Now we move around the room, and now on the other side, the total opposite side of the room, there's a couch, and you can kind of see the arm of the couch here that's partially consumed. And then there's a coffee table in the middle of the room, and then there's an end table on each side of the couch. Again, white discoloration high in elevation, consistent with an upper layer or hot gas layer generated pattern, no big deal. Pretty simple fire pattern. But when we move to this wall, that's where it's like, like I'm pretty good at fire patterns. I'm pretty good at seeing things, but that's hard, right? Because pretty much the whole wall is now white except for the corner behind the table. So by the visible observation alone, that doesn't really give us a great area of damage. Now I can see some discoloration here in the center, and then where the arm of the couch leaned up for a protected area, and then maybe a little bit lesser damage over here, discoloration by the hallway. But just by itself, visibly, it's hard to kind of discern exactly on that wall what's going on. And we go to the fourth wall, and that's all high elevation damage too. So I think if I was to survey everybody right now on the call, everybody would say, well, you're probably over here to the left of this image, close to the couch, not the love seat. I don't think that's probably a difficult task for anybody. But when we take the actual measurements and we kind of display it. So here, what I've done is they call that an exploded view diagram. So basically you've taken your two-dimensional floor plan and you just exploded your walls out, so they're laid down right now. But these are elevation views. So here's your door, that's your outline of your door, and then here's your window, and then behind your love seat, you can see you have a protected area. The brighter the color, the deeper the measurement in this contour plot. And so if we go to the wall that was of interest to us when we saw visibly where our couch was, there is the center of that wall that is a bright color. So that's telling us high or deep measurements of depth of calcination here. But then there's something going on at that table. Now that is the actual origin. We actually started the fire underneath this end table, and then it obviously transferred into the couch and burnt, consumed the couch. Now, would that one little pocket of damage behind the table be enough for me as a fire investigator to say, aha, that's the origin? Probably not, but it would make me stop and question a little bit more compared to just looking at the visible damage alone. So that's I think the intent behind us doing depth measurements is that when we visibly can't see differences, measurable data does come into play on some of our scenes. Here's my students did this one. They basically took, I think this is Google SketchUp. When Google SketchUp was, I think it was still, I don't know if it's still free or not, but it was a 3D diagramming software. And they kind of just overlaid an Excel spreadsheet graph. And that was a different way of kind of showing depth measurements. And I thought that was kind of an interesting way of displaying. So I guess what I'm trying to tell you is there's different ways to display your depth measurements along the way that kind of help visualize for others what's going on.
Sorry, great question.
Yeah, absolutely.
Just that last room that you showed displayed, not that one, the one before. How long post flashover did that fire burn for to produce those patterns?
Yeah, no, that's a great question. So this one would have went 2 minutes post flashover.
Okay, great.
Yep.
So yeah, obviously the initial patterns are gone, and you've got that full calcination on all four walls. Yeah.
Yes. Yeah. Yep.
Thank you.
Yeah, absolutely. And so one of my dissertation, and I'm going to bore you with that, but my dissertation was focused on how do we better use fire dynamics in the context of interpreting fire patterns and how these patterns and damage are created. So one of the things I found in the fire investigation profession that we've never done a great job of was, well, how do we all agree? Do we agree on varying damage like initially? Because if we don't agree on just the fundamental data, then we're going to have real problems when it comes to the interpretation, right? We'll never agree on the interpretation if we can't at least fundamentally agree on the data itself. So what I did is something silly, and it ended up getting published in the Journal of Forensic Science, but I wanted to say, okay, what if we just number the damage, right? So a 0 would be no damage at all. It's your clean gyprock. 1, you're starting to get soot deposition. 2, you're starting to char the paper. And then 3, we're starting to pill, bubble, and flake that paper off. And then your 4 and 5 kind of gets into we're burning off that paper, and then we're getting that clean appearance where, depending on the drywall or the gyprock, could be a white hue, a color, blue, or pink. I've seen it just depends on the manufacturing process and the materials they're using. So I just went through and numerically assigned what fire investigators, most fire investigators are seeing in differences of damage, and I came up with a silly little degree of fire damage scale to just kind of say, okay, well, a 0 means this, and this is what it looks like. And so I provided this chart to it was a bunch of my students, right? So they're fire investigation students who had training and stuff. But what I did is I gave them a grid, and I said, and I'll show you, it's a different wall than this one. but it's this wall here. It's a similar test fire to this, so the damage to that wall looked almost identical to this. The only difference is the wall was painted orange, so instead of white, you have an orange color. But the point is I gave them this, and I said, okay, I gridded it off, and I told them just on their own, just on your own understanding of differences in damage, you identify each grid space based on the level of damage you think, and use a number scale from 0 to 5, right? And go. And so they did it, and they were all over the place, right? Because the way one student defined a 1 or a 2 was completely different than the other student, which shouldn't be surprising when you don't give them a method. They use their own method, right? And I think that's what happens a lot in fire investigation when we're looking at varying levels of damage. Some people say, oh, this is greater and this is lesser damage, but we don't have really any good definitions of what that is. So what I wanted to do is provide them, okay, we have a picture, and this is the numerical value. And I don't care if you use numbers or not. That was for my statistical analysis. I was using numbers. But once I provided them this, I had them redo that same exercise, and lo and behold, all the answers started to collapse. So instead of, each student having varied numbers, a lot of them started coming up with the same numerical value. And that's so simple, but that's actually really important for forensic sciences, is that we at least agree on the data. So I do think this is there's something here. And so anyway, that was one of the directions I wanted to go with my dissertation, is how do we make this more objective? And that's kind of where we get into some of the depth measurements. Now, I don't like the terminology we use because it's too vague, like heavy damage, major damage, severe damage. We all use our own little terms. But the problem with that is that you may say major damage and I see it as minor damage, whatever the difference is with that. But how can I, as an expert, come behind you, or an analyst come behind you, and agree that we fundamentally understand the same data? So if you like using the vague descriptions, which I'm okay with because I'm not a big fan of the number system that I just provided you, but if you define what it is you see, I think that's really helpful. And so that's kind of what I was showing here, is you can use these terms, moderate damage, just define what you mean by moderate. So when you're writing your report, somebody behind you can say, okay, I get where they're coming from with moderate on this wall. So there's the publication, but that led into basically how do we use this varying level of damage as it relates to patterns? I'm going to jump over this stuff. And then where does the application come in? So depth of calcination is one of the stronger processes that 921 talks about, because we've had a series of scientific research into the mechanics of depth of calcination. And then we've also had several over the years where they've looked at, okay, how do we apply this to the actual scene work? And I think that's what makes a solid process for a fire investigation, right? We have the science backing. We also have the application that shows that it works and how we use it in our scenes. So that's one of the reasons we went this direction. So our research for the grant work that we did 3 different exposures to heat. We had a radiant heater, so this left picture, and we exposed drywall or gyprock to a variety of lower heat fluxes with the radiant heat flux. And then we went up to 100 kilowatts per meter squared with our premixed flame source, which is basically a torch. And then we also did a diffusion burner as well, which basically that's a sand burner in which we're exposing just your diffusion flame against it. And we would take regular measurements. So every minute we would take a measurement of the depth of calcination. And internally, so the way we had it set up is your gypsum wall board is, we used a 1/2-inch drywall, which is 12.7 millimeters. So we would expose heat to one side, and then we would take measurements obviously from that same side. But behind the drywall, which is, I think I have a picture of this later. You can kind of see it here. We actually poked in our thermocouples for every millimeter. So we had one at the surface monitoring actual surface temperature, and then we had one every 1 millimeter into the depth. So we were able to track that dehydration front and that temperature profile throughout the thickness of the drywall, as well as get depth measurements during the actual exposure. We had to do what they call a thermogravimetric analysis, or a TGA, differential scanning calorimeter, or DSC, and then we also did your Fourier transfer infrared spectroscopy. And all that's to say, basically, we were looking a little bit deeper at the chemistry and the different heating rates of the drywall. So we would take sections after we exposed them to heating, and we would send those off to a different group that was Georgia Southern. I don't know if you saw that university listed on the front slide, but we would send it to them. They would run this stuff and give us some of the understanding of the heating rates and what kind of dehydration each of these samples were given. And then they ran some of their own studies just with standard heating rates to see what is that, the chemistry behind this dehydration front. And that was basically to set up where we were going with our mathematical modeling. So here, just as an example, I'm giving you some of the experimental results. We tracked the temperature. So your high temperature here, that's at 0 millimeters. So that's at the face where it's being exposed to the heat. And then every millimeter internally in the drywall is being tracked with temperature. And then on the right, we're showing you that contour plot of that temperature difference throughout. This is our standard deviation. So it's not horrible, but experimentally it falls within, what we would normally find for most experiments with fire. Fire protection engineering, we're plus or minus 30%, we're happy. So this is not overly bad on our standard deviation. What we're looking at here is the temperature of the dehydration front. So what we did find is, I went into this whole series of experiments thinking, fire patterns are essentially the history of heat flux. And so I thought, well, if the higher the heat flux, the greater the damage. That's true, but not true. And that's kind of what this is showing you. You have to reach a certain temperature before you really start influencing that dehydration front and then ultimately what we're measuring. So if you don't reach that temperature, that critical temperature threshold, then you're never going to see a dehydration front go through the drywall, which makes total sense. If it's 1 kilowatts per meter squared and you expose it for 24 hours, that's not going to dehydrate the drywall because you're not reaching the temperatures to drive the water out. So that makes total sense. And that's kind of what we're seeing here. Once we hit that threshold, whatever that heat flux is, then we are seeing that heat flux history play a role. But you have to, at a minimum, hit a certain temperature for that threshold to take off. And so where the TGA results, we saw it's not a linear graph. So there is something that happens throughout the drywall, and it makes sense, right? You start heating up that water, then you have to essentially evaporate that water, but now you have this moisture that's going to play a role in moving through the drywall. And so there is a difference. Once you drive out a lot of that water, then your temperature is going to do some interesting stuff, kind of plateau out and do and keep going. And so that's kind of what we're seeing here, is that you got to push that whole dehydration, that water out, and then you're going to really start affecting the gyp rock. And so from a mathematical perspective, what we were really focused on is this species and momentum conservation. And I know everybody that just probably looked at this screen is done listening, but just we'll get through this if you're not fun, if you don't like math and the chemistry. But what we're trying to do is we're trying to get this data on, heating rates and understanding what's going on from the chemistry standpoint, and then mathematically applying that so that we can have some valid prediction methods. And so we're looking at the species conservation, where we're looking at, that water dehydration front through the momentum of that. And then obviously it comes back to the energy conservation as well. But a big focus of ours was this value here. And that's really your vapor production rate. Like, how fast is that happening, and how fast are we moving that moisture out of the drywall? that's going to slow down or speed up this whole depth of calcination aspect. So you have these two points where you're pumping in a lot of energy and not changing a lot, and then you plateau and then you go through it again, which makes sense from the standpoint that we were talking about the physics earlier. Is you're exposing this drywall, you got to dehydrate, and then you're pushing that water essentially out of the drywall, and then you're affecting the gyprock. So that's kind of what we found in previous literature, and we found the same thing when we were doing our experimental work. What's of interest is we wanted to match our experimental to the numerical results. So we're really checking and tracking this numerical aspect because that's the prediction side. So can we better predict? And so, not to bore you with all this stuff, too late, right? We wanted to kind of show that the experimental is or is not matching our numerical predictions, and we are seeing, as you can tell here, that the stars, right, is our experimental data, and then that red line is our numerical prediction. So we're adequately or accurately predicting, based on the chemistry that we now understand, what we would expect from a prediction standpoint numerically. And so there's a little bit more of that data, sorry, I jumped over those. We're showing you different heating rates. So the faster you heat it, it's going to affect the faster that numerical prediction is going to be, which makes sense. So we really focused on that vapor production rate, that Q dot M, that Q dot with the lowercase m. And then that helped us go into our numerical methods. Now, the gentleman who's on this with me, his name is Dr. Shijin Kajamal. He is from India. He's one of the smartest numerical guys I've ever met. So he's the brains behind this. I understand it vaguely, but no, he's the focus. So we did a couple things here. We applied this mathematical prediction model, and we looked at it from an experimental standpoint, and we're checking to make sure our numerical prediction is matching what we're finding experimentally. And then what we had to figure out is, so heat transfer goes in 3 dimensions. We understand that, right? It's going to go your X, your Y, and your Z as you're heating through this drywall. It's not just one direction, as I keep kind of talking about. It goes in 3 dimensions, but 3-dimensional modeling is really difficult because it takes a ton of computing power to do that. So what we were trying to see is we did some 3D modeling to see, do we have to model this as a 3-dimensional problem, or is the 1-dimensional problem approach acceptable? And what we did find is that the 1-dimensional approach is an acceptable method for drywall, for heating of the drywall.
We do have a question online for you just in regards to the moisture.
Oh, yeah.
From Grant, is there a bias in which the direction the moisture is driven, and does framing have an influence on the loss of the moisture and decalcification?
Yeah, so good question. And that's what we were looking at here. We wanted to know, is there a substantial amount going in the other 2 dimensions, the other 2 directions, that we have to take account in our mathematical prediction? And no, what we're finding is that when we model it as a 1-dimensional, like 1 direction heat transfer, it is adequately predicting that dehydration front. So yes, in the general physics, you are correct. It is going to go all 3 dimensions, right? It's going to go out the front as it's heating. It's going to go pushing through the rear, and it's going to go through the actual board itself. So yes, from a physics standpoint, that does happen. But what we found from our experimental and then connection to our numerical, if we just focus on what's being pushed out from the 1 dimension or 1 direction, it's adequately predicting that dehydration front. But you are correct; it would be all 3 dimensions. So then we went into that validation aspect. So this is just a bunch of graphs that's going to bore you, but the point is I guess the takeaway here is we have a numerical prediction, and then we're comparing that to our experimental data. So the weird figure or weird things, so your stars, your X's, your triangles, your circles, those are your experimental data. and then the same color but solid or dashed lines are representing what we're seeing numerically. And so this is a heat flux of 10 kilowatts per meter squared. So, a low temperature hot gas layer kind of exposure. And then here we're at 50 kilowatts per meter squared. Now, when you get into 50 kilowatts per meter squared, you're starting to see a little bit of that diffusion flame, lick across the drywall. But you can see that our numerical and experimental data are, similar, not perfect, which we would never expect it to be perfect, but similar, which is good from a prediction standpoint. And here's 90 kilowatts per meter squared. So now this is, flame up against your surface exposure. And so we would expect flame against your actual exposure to be harder to predict because that's a lot of heat and it's there's a lot that's going on and it's fast. So our numerical is still matching the general trends, which is good. We did a whole sensitivity analysis. If you want to get into the math on how we came up with stuff, well, I can provide that to you, but I'm not going to bore you guys on the presentation. And then this is where we looked at three-dimensional. So we are able to model three-dimensionally, and you can see that we can adequately see, that's going on. But again, the computing power and just the time it takes to do this is pretty substantial. But it isn't considerably better than the one-dimensional approach that we were doing. And then we moved into correlation. So a correlation, as I always have to teach my students, is basically, and hopefully this isn't mansplaining, you guys can yell at me later if it is, but experimental correlation is essentially you're taking that experimental data and then you're essentially putting an equation to the best fit line curve or exponential curve. And then that curve is what we then can apply. So we found two different fits to that. You have your experimental and then you have your numerical. So basically you can take this equation and it could predict what they would expect to get for depth measurements, or vice versa from a fire investigator standpoint. If we take a measurement, say it's 9 millimeters in depth, we can help predict now what heat flux exposure was seen at that location, which we feel could be helpful for fire investigators. One of the big takeaways is, when you get into that 50 plus kilowatts per meter squared all the way up to your 100 kilowatts per meter squared, we can tell you that if you're 8, 9, 10 millimeters or more in depth, you saw a high heat flux. So you probably had a flame against that wall at some point in time. Now, that doesn't tell you that's the origin. It just tells you that you had flaming combustion up against that drywall at some point in time during the duration of the fire. We then wanted to connect that to, if we have these measurements, can we put this in actual computer modeling? And so we feel, yes, this is a direction we can go, which from a fire investigation standpoint, this is FDS. We use FDS. And we just did heat flux boundaries on the wall surfaces, and then we compared that to our depth measurements that we did on a full-scale burn. And then we did our numerical and experimental correlations to show what we would have predicted based on the values that we're seeing there. And you can see that the trend is very similar. And from a fire investigator standpoint, that's the most important thing. Yes, we do care it's plus or minus whatever from a scientist and researcher standpoint, but from a practical standpoint, are we getting the similar trends? And why that's helpful to us is that we think they're in the future, we're not there yet, but in the future we might be able to model with this heat transfer boundaries and test different origin hypotheses based on depth measurements that we found on the scene. So that's kind of a direction I think some of this data can go. So that's the first stage of research. Sorry, go ahead.
Sorry, just to jump in again. Another question from Jim Monday online. Is this time dependent? ED 50 kilowatts per meter squared heat flux for N minutes gives the same depth as 100 kilowatts per meter squares for in 2 minutes.
So great question. That was when we went into this, that was my my thinking, right? That was my hypothesis when we went into all this research. And what we found is that's kind of true, but not always true, right? You can't have a low heat flux that you expose for 2 hours, and it's going to give you the same thing as a high heat flux, say 50 kilowatts per meter squared for 2 or 5 minutes, right? That's not going to equate unless that threshold for temperature is met. So if you're not having high enough temperature to dehydrate the water, then you'll never get the drywall calcinating, right, where you're actually being able to get depth measurements of any sufficient value. But when you get to that high of a heat flux, yes, then it will be somewhat dependent on duration. And so you'll see that kind of with our correlations, that time does play a role in this a little bit, but not as much as I initially thought for your lower heat fluxes. Great question. So the second phase of research, we focused basically on all the other types of drywall. We did different paint layers. We did on just general normal gyprock. Then we also did your fireproof, your waterproof or moisture proof, your soundproof, a bunch of different drywalls. The interesting thing about the drywall, where they have all this, different branding and names, essentially what they're doing is they're adding additives or they're adding a lot of fiberglass materials into it. And so we kind of went into this guessing, our hypothesis was that's going to affect our depth measurements. And, long and the short of it is it does. So we are struggling to come up with solid correlations on these boards, but we think there is something there. It's not as easy as just your normal gyprock. And so, again, the objectives of the second phase was take this different types of gypsum material for different types of lining materials. So I'm assuming you guys also run into something similar there, where you use like moisture resistant and soundproof and those types of drywall or gyprock as well. So we tested that. And we also did scanning electron microscope analysis, so an SEM analysis, to see, because if it's a dehydration front, are we visibly able to see that there was dehydration? And so that was one thing that we added to this research as well. So I'll kind of give you highlights on that. But basically, we do have a lot more deviation, right? So it bounces all over the place compared to what we were seeing we had a much nicer, from a research standpoint, more smooth curves, and our prediction was much closer. When we actually sit here and do all these different types of drywall, we're finding that it's going to bounce a lot more. And that is very dependent on all the fiberglass reinforcing a lot of this material. And so that's affecting our depth probe measurements. So it's not as effective as your normal drywall. There is something there, but you really have to understand the various additives. So you got your glass fiber, your metal alloys, what amount of this material is in the drywall, and then how that affects your depth probe measurements is not completely understood, and we are working on better understanding that. It's not a heat transfer. There's not enough material in there to really affect the heat transfer. So we're still getting that dehydration front, and all the math that we did on the chemistry side, that's still working. The problem, though, is when we're taking our measurements, we're hitting these metal alloys, these fiberglass reinforced, additives, and that's affecting our depth measurements. So there's something there, but we haven't quite figured it out exactly yet.
From the online guys, wallpaper in older homes, did you find any correlation for complicating your depth measurements there?
So we didn't do wallpaper, but I have seen a recent study. It's not published yet. It might be coming out. That somebody did use wallpaper, and what they found, it didn't really drastically affect depth measurements, but it does affect, because you have the flame spread on the front, your visible pattern will be could be substantially different than a non-wallpaper, but your depth measurements were still matching up, which to me that's a a better sales pitch to why we should do measurable, especially when we have wallpaper, is because the visible might be from your flame spread across your paper, not necessarily the actual heat exposed. And so the heat exposed could be still tracked by measurable data. So I think that paper is probably going to be published. It was from another set of researchers, so I don't know all the details, but from what I saw in their research so far, that's the direction they're going with some of that. So our experimental setup was very similar. I don't have to go through that again. We exposed it. The only thing that we did differently here is we didn't do a diffusion burner. The diffusion burner is all over the place. So we had a lot of discrepancy in heating, which is expected, but that's also what we're going to find in the real world. That's why we wanted to do that study. But now in our second set, we chose just to focus on constant heat fluxes. Here's your scanning electron microscope images. So we took SEM images, and you can actually see in an SEM that dehydration aspect that we talked about throughout the day. So I think there is some value here. We didn't do enough work, I think, to get there yet, but we're planting the seed, and hopefully somebody else can, pick up this ball and run with it type aspect for future research. But there is something here. And then the other thing that we did, and we're still working towards this, is, again, my focus is objective. How can we be more objective in what we see? And so I think artificial intelligence, especially when it relates to like digital image analysis, is a direction fire investigation can benefit from. I think there's a lot of things that it can, help us. One of which is how do we identify lines of demarcation? Because oftentimes we get on a scene and a fire investigator is talking about, well, I see this, and another one saying, well, I see this. And I'm not saying either of them are wrong. It's just, how do we have a system where we all see essentially the same larger lines of demarcation, right? We're never going to take interpretation out from the individual person, but how can we better, identify the similar stuff? And so we applied this. We published this article. That's what this is here. We published it in International Association of Arson Investigators, or Fire and Arson Investigator. This is a few years ago now. But what we did is we used digital image analysis, just your normal tools that are out there, to see if it could identify lines of demarcation. And so the image we're using is just a single. This was a recliner on one of those overstuffed polyurethane foam chairs. We burn it up against a wall surface, and then we're seeing if digital image analysis can kind of pull out the larger lines of demarcation. And so there's a bunch of different tools that are currently available that do just not lines of demarcation for patterns, but where they're able to identify the larger changes or gradients in color, texture. There's a variety of different tools that are out there and this is how a lot of your picture, if you use your phone or a camera or, Adobe or anything like that, it gives you options to kind of, I don't want to say manipulate because that's a bad word, but modify your image, smooth it or just increase the quality of different items. These are the tools that they're using. So it's just a mathematical tool. If you think of a picture, a digital image, it's an X and a Z, right? So you have two axes, and then your pixel value, two axes, let's say X and Y. So you got your X axis, your Y axis, and then your picture is just a bunch of pixel values. So 0 to 256, or however you have this set up, if that's a color image. But anyways, those pixel values are all numbered, right? And so that's a matrix of numbers. That's all that is when you look at it from a digital image standpoint. Like, think of the matrix type thing, right? So you just have a whole bunch of numbers. That's essentially what a picture is. So because there's differences in color, there's differences in texture, can we use math to say, okay, there's a big gradient change between these two colors. Is the digital image analysis able to identify that objectively? And so that's kind of what this was setting up. And so we use the standard tools that are available out there in all your digital software, image analysis software. And then we compared it to an artificial intelligence. So we created an algorithm for it to identify using some of the tools that are currently there. But we created an algorithm to say, okay, can it find these lines of demarcation, ones that are actually important to a fire investigator, the big discrepancy. So for us, these red lines, just see if it could find these versus the blue lines, which weren't important from a fire investigation standpoint. Is it able to identify that? And so what we're showing here is there are these different tools that are out there. So these are different algorithms. So Canny, LOG, Pruitt, Roberts, Sobel, and their ability to accurately identify those detections, those lines. And so these are your percentages of accuracy. Our AI was much better. So it's at 78% accuracy at identifying the lines of demarcation. So we think the more training data that the artificial intelligence has for you, so training data is basically a bunch of photos, right, where we know damage. Is it going to be able to identify objectively the different lines of demarcation, at least the larger ones? And we think there is something here. So even though this isn't depth measurements like what we focused our research initially on, it is something that is a better way of objectively identifying damage, right? Varying degrees of damage in pattern analysis. So that was kind of the future direction of some of the stuff we're doing. And then here's my shameless plug. If you haven't voted, vote away for IWI director. That's I am running for that. So let's see. Stop sharing. All right. Sorry, I wasn't able to see the chat button because my screens were all taken over. But if you guys have any questions.
Yeah, if anyone's got any questions, just raise your hand and then we can do it one by one. I've got a question for you, just in regards to the program that you do at Kentucky University there. How long has it been running for now?
So the degree program started in 1973.
Oh, that long ago.
Yeah, and the investigation started, I would say, 15 years later. So in the 80s is when the actual investigation degree started. But 73 we started. We have 3 different degrees, the engineering technology. So those who want to go out and design systems, that's kind of how we started.
About the fire investigation one.
Yeah, so that would have been in the 80s, mid 80s.
Yeah, okay. And what about like the current students and stuff? Have they gone out into the world? How many students?
Oh yeah, they're everywhere. We have an online and on-campus degree now in the investigation. The online requires residency, so the students come in for 2 different 7-day weeks over. Usually it's the summer, but we have several. So we had several students from UAE, Belgium, Germany. So we've had a lot of international students also, and which is really cool because we get everybody in one room. You got people from the States, you got people from international, and so everybody's learning from each other, and that's a lot of fun. So we've been doing the online one for about 10, 12 years now. But the original degree, was in the 80s.
Yeah, and do you think AI is going to play a major role in burn pattern analysis? Like with
AI?
Yeah.
Yes, I do. Very much. I envision someday, and we're not too far off of this, being able to take a picture with our phone or our tablets, and it able to identify right there on the scene those major lines of demarcation.
Yeah. We do have a question. So was humidity one of the variables measured during testing?
Yeah, good question. We did. So we made sure that we had humidity the same for all of our drywall. So we didn't vary that. We kept that as a control. We do think that humidity will play a minor role because there is some free water in that drywall, but it's not so much that it's really affecting that dehydration front. The next series of questions that somebody probably should have would be, well, what happens when water sprayed on it from fire suppression? And there was a research back in the day that was done by a group out of Seattle where they did re-expose calcined drywall to water, and it does not reabsorb, right? Because it's chemically dehydrated. So you're not reabsorbing the water. But if any fire investigators on here, they know if you have exposed water for a long duration to that drywall, it's going to be mush at the end. So eventually that will have an effect, but it won't rehydrate the drywall. So depth measurements, as long as it's not mush, your depth measurements should still persist even with exposure to sprinkler water or fire suppression water.
We've got a hand up, Jan. She wants to ask a question.
Yeah, thank you. Just a question about one of the graphs where you had the second type of drywall, if that makes sense.
Yeah.
It appeared at one stage that the depth of the charring would decrease, like it would go down and then would go less. Is that because it burns away and then you have less, like the surface is less?
No. So when we're taking those measurements, it's not the exact same spot, right? Because we don't want to have the probe in the exact same spot every time. So we're moving the probe slightly, right? But so it's not in the same hole, which means what we're probably doing is we're hitting fiberglass in one and not the other. So that's where that discrepancy is coming in. So you have metal alloys and fiberglass in those reinforced different types of drywall, and that's affecting that depth probe measurement. And so we think that's having a bigger effect than the dehydration front.
So it's an artifact rather than actual.
Yeah.
Gotcha.
Yeah.
And another question, if I may, about the same graph. The lowest graph looked like it was basically stable. So you had the initial threshold temperature, and then you basically the depth of the charring was the same for the whole, however long you did it. It became it was the same for the whole time. Is that correct?
Yeah, when that goes back to that, are you getting enough? Are you getting high enough temperature to drive the water out to begin with? And if it's too low of a heat flux, you're not going to get that dehydration front moving through the drywall. So I think that's what we were seeing in that.
Gotcha. Thank you very much.
Yeah.
Is there any other questions for Greg?
There's one more on the chat there, mate.
Oh, sorry. Let me have a look. Got to bring that back up. Maybe it's the very start of. So you may have covered. It does a hydrometer that the flood and moisture assessors use help indicate the calcification. I think like a normal.
So we didn't directly measure humidity. We maintained the same moisture content to keep that as a control. So we do think, yes, moisture content will play a role. And we know what the moisture content is. It's 21% by mass is what your normal chip rock will have of water. So we know that. Will extra humidity or higher humidity affect it? We think it might a little bit, but not substantially, because you're not driving out the free water. There is free water you're driving out. So that's where the effect of humidity would come in, but it's not substantial. Where we're seeing the depth measurements, we're actually getting the crumbly material is you're chemically dehydrating it. So the humidity itself is not going to greatly affect it, but it will a little bit. I think he was asking, like, can you use the actual moisture measurement tools that people use? Can you use that to get the correlation? Well, you can measure the moisture content, but it won't tell you calcination within the drywall. The best way to do that is either through an SEM or through the depth probe method that we're currently using.
So it's the probe method is the most acceptable.
So far that's the best method of figuring out.
Yeah. Any other questions?
Yeah. I was just going to say, thanks a lot, Greg, for coming online. I know it's early where you are. I think depth of calcination is certainly a topic sort of probably not understood fully in this country. I certainly don't know too much about it, so your presentation was really good. So I do appreciate your time. I would like to say that, certainly I've asked our members, IWI members, to vote, and I voted for you for sure. But and when you get onto the committee, the board, which I know you will, we need to sort of look at, I guess, the international side of the IWI, not just the North American side of the IWI, and get an ITC outside North America. What do you think?
I'm with you. I went to the European Association Fire Investigation this last year and taught in Dresden, Germany.
Yeah, that's awesome.
I told them the same thing I'll tell you guys. I definitely think this international association should be more international. Absolutely. So the more we can get everybody involved, the better the organization will be. So absolutely. And I'd be more than happy to fly out there.
IWI is rich enough. Forget about the cost. Let's just do it outside North America. Are you with me?
Yeah, I'm with you. Yeah. 100%.
Well, I'll probably see you in Reno next year. I'm not there this year, but hope it all goes well. And thanks a lot for coming on early in your time to present to our little tiny chapter of New South Wales in Sydney, Australia. Thank you.
We have a lot of members from the other chapters down under as well.
I know, but this is a New South Wales AFI education night.
I appreciate the invite. Thank you.
Yeah. No, I appreciate it. We'll send you out a coin. I'll get your address, and we'll send you out a little gift.
Yeah, challenge coin
for doing this for us. If there's no other questions, we'll wrap up the meeting. And once again, thanks, Greg, for taking the time to present for us. Appreciate it.
Absolutely.
Thank
Thanks.
you.
Take care.
Cheers, guys. Bye.
See you later.